Hello everyone. Good morning. My name is Nafisa and I'll be starting the presentation for my group. Our topic is titled Energy Efficiency of Buildings, and these are my team members, John, Nadir and Arsala. So for our table of contents, I'll be covering the introduction. We'll be covering the introduction, the objectives, our solution and the results that we currently have. So first of all, what is energy efficiency? Energy efficiency refers to the use of less energy in a building to carry out the same operation that a normal building would carry out efficiently. And energy efficiency needs to be considered during the construction phase, the design phase, and also the operational process of the building. So you have to consider energy efficiency across board throughout the entire life cycle of the building. What does energy efficiency in a building mean? It means that we're using energy efficient equipment, we are integrating renewable energy technologies in different applications, we're using low embodied energy building materials, and we're building nearly zero passive building design. So energy efficient buildings on the EU approach. In 2019, the EU overall their energy policy, so we're trying to move from fossil fuel into cleaner energy, and the building sector is one of the major areas that the EU is considering to realize its energy and environmental goals, and that is why it's very important for us to integrate energy efficiency into the entire building process. Today, we know that buildings are responsible for around 40% of energy consumption, and they are also responsible for 36% of CO2 emissions in the EU, and this makes them the single largest energy consumer in Europe. So it is necessary for us to take into account the energy efficiency of buildings, just like I had mentioned earlier. And this visual is just showing the pictorial representation of just what I have explained now. So for our objective, the goal was to use 3 SSIO sensors to measure the temperature inside the building, outside the building, and to place another sensor just beside the material to measure how much temperature is being recorded for the different materials and the temperature inside and outside the building. And after getting the data, we intend to calculate the U value, which is the thermal transmittance of the different materials. So in our case, we've considered wall, glass, and metal. And after doing that, we would compare the results and give a clue as to which of the measure gives the best performance and which one should be considered going forward. For our solution, just like I had mentioned, the goal was to calculate the U value, which is also the thermal transmittance. And U value, in simple terms, it means when your U value is closer to 0, it tells you that the building is well insulated, and the material that you're considering, or the material that gives you the lesser value to 0, is the best material to use when constructing a building. But when you have a value that is very high above 0, it tells you that the material is not well insulated and you should not consider those kind of materials when building. In our own case, we've considered the thermometric method to calculate the thermal resistance U value, and that's the formula right there. So it's just Q, which is the heat flux divided by the temperature in and the temperature out multiplied by the heat transfer. And for the heat transfer, we have the formula over there. So at the end of the day, we realized that the ISO has a standard, ISO 6946, they have a standard for RSA, which is 7.69, and that's what we're using as the constant to calculate the U value in our case.
So this is an architectural diagram or experimental setup where we are using 3 different loci for sensors and placing one for the indoor, for calculating the indoor temperature, the other one to get the temperature of the wall, and the third one for outdoor temperature. But since we had only 3 sensor kits and we also had to do comparison between different materials, so we used emulated values for indoor temperature and we got the outdoor temperature from an API, and then we are aggregating those values, everything to a cloud platform that we will use, and we will be displaying those results in real time. So some of the results, so this is how our dashboard looks. So for these values, we have done the experiments on the wall that you see on your left. So basically we have calculated the values for glass, metal and wood. So based on the setup that I just explained, we got these new values for the 3 different materials. So as Nafisa explained, the lower the U value, the more insulation the material provides and better for energy efficiency. So wood U value is around 1.01. The one for the metal is highest, which is bad. For insulation it is 2.67, and the one for the glass is 1.39. And like calculating a rough area for this wall, we have and like percentages, we got the area for individual materials that is used in the composition of that wall, and based on that we are getting the energy loss per year in kilowatt hour. So this is the energy loss through this wall. If given this condition, this building is like run for 365 days, so that will be the energy loss per year. And then using the cost per kilowatt hour in building, we are calculating the electricity cost for that, and that is in euros. So right now, if you see, the metal only constitutes around 2% or 3% of the wall, and which is only part of the door. And wood is also quite less, which is around 7%, but 90% is glass. So that's why most of the electricity cost is because of that. So if you use a different material instead of a glass and one with a lower U value, then the electricity cost would have gone down, which would have been better. And from the dashboard, we have also a map which right now just uses some random values to show the location of the sensors, but ideally we would want to do indoor localization of the sensors so that you can track and monitor the location of your sensors in real time through the dashboard. And you can also view some historical time series data, which here is outside temperature, the top one is the inside temperature, and this one is just inside the wall, and this one is for glass. So some limitations in future work. So the results can be made more accurate with temperature sensor that can be directly attached to the wall surface. So right now we are using sensor kits which are placed just beside the wall, but ideally you would want temperature sensor to get attached to the wall in order to get the accurate temperature. And then again, as I mentioned, you would want indoor localization of the temperature sensors so that we can track and monitor them through the dashboard. And that's all from our side.
I think you made a very good work getting lots of background information about energy consumption and what EU thinks is and all that. Great work. More comments?
Quite useful because we always think about the materials and you can actually see that in implementation. You can reduce. Because there's one thing that we think is going to be like this, but if we have these sensors, then we can actually know
Yeah, I think
what the consumption or the losses or how it is.
For me, it's like a trade-off between aesthetics and like electricity cost, because I think the use of that many glasses is more for aesthetic reasons that you can view, and also maybe for sunlight coming in. But if you can reduce some of the glasses and make them like replace them with good well-insulated materials, then I think the heating cost would go down in a larger scale.
Any more comments? If not, thank you very much.